So this is a little bit more complex example. Now we're changing 1.03 kilograms of water from ice into steam. So we have not only multiple phase changes going from solid to liquid and then from liquid to gas, we also have temperature changes in there as well. So it would help to graph this out to see exactly what's going on. Try that one more time, just a little bit straighter line. So the scale on this doesn't matter. We have our water that begins at -5 degrees Celsius. It will melt at 0. It will boil at 100. And our time finishes when this water hits 120 degrees. So from -5 to 0, the water heats up, the temperature goes up. Then the temperature remains constant for a while that ice melts into liquid water. Temperature rises again until it hits 100. Stays at 100 for a while it turns from liquid into gas, and then rises until it hits 120 degrees. So we actually have 5 different calculations we have to do for each of the 5 different pieces of this change. Now, why can't we just do one calculation? Well, because the latent heat in sections 2 and 4 is different whether the water is melting or whether it's vaporizing. As well, the heat required to change ice's temperature is different than the heat required to change liquid water's temperature, which is also different from the heat required to change the gas's temperature as well. So this is going to require a combination of Q equals N delta H, as we've been looking at, as well as Q equals MC delta T, which we looked at in the last section. So for section 1, the heating ice, that's a temperature change, so we'll need Q equals MC delta T. The mass of the water, 1.03 kilograms. C for ice is 2.1 times 10 to the 3. And delta T, all we care about is that small 5 degree change when it's still solid ice. Multiply that out, and right now sig figs don't matter because this is just one small section. We get 10,500 joules. I'm going to deal with all the temperature changes in one shot, so we'll do section 3. This is the liquid water heating up. So again, we'll need Q equals MC delta T. The mass is still 1.03 kilograms. C for liquid water specifically is 4.2 times 10 to the 3. And now this section in here is a 100 degree temperature change. Multiply that out, and we get Q is 432,600 joules. Just have to flip the slide to do the rest of the calculations. We'll do section 5, the last temperature change, when the water is already heated to steam. So mass is still 1.03 kilograms. C for steam is 2.0 times 10 to the 3. And the delta T in this section, it's going from 100 to 120, so delta T is 20 degrees Celsius. Multiply that out, and we get that Q equals 41,200 joules. The last two sections we'll deal with are the actual phase changes. So section 2, going from solid to liquid, that's a fusion. It's a phase change, so we need Q equals N delta H. N being the mass, still 1.03 kilograms. And delta H fusion for water, 3.3 times 10 to the 5th. Multiply that out, and the heat required for this section of the heating is 339,900 joules. I'll flip the slide one more time to do section 4. This is the liquid water that is vaporizing into steam. Again, phase change, Q equals N delta H. The mass of water hasn't changed in this whole time, 1.03 kilograms. Delta H vaporization for water is 2.3 times 10 to the 6. And we get that Q is 2,369,000 joules. So now we can find the total heat required for this entire operation, which would just be adding up all of the individual heats. So the 10,500, the 432,600, 41,200, 339,900, and 2,369,000 gives us a grand total of 3,193,200 joules. Which, of course, we need to now go to sig figs. We have 2 sig figs as our smallest in any calculation, so we would round that to 3,200,000 joules.